Jai Hind to all. I am Shivpratap Singh, Assistant Professor, Department of CSE, Ajay Kumar Garg Engineering College. Today, our topic of discussion is graph, in which we will explore the representation of graph, as well as we will explore the minimum spanning tree algorithms like Kruskal's algorithm, as well as we will discuss Prim's algorithm and solve a numerical problem how to find a minimum distance between a set of vertices or between a graph vertices. So, let's cover all these topics one by one. So, a representation of graph. So, to represent a graph is a data structure that consists of set of vertices or called nodes and set of edges. We all know about this. A graph is a collection of vertices and edges. We can say a graph is a set of vertices and edges. And there are two ways to store graphs into the computer's memory. First is sequential representation, or we can say adjacency matrix representation. And second one is linked list representation, or we can say adjacency list representation. So, if we talk about adjacency matrix representation, so matrix V by V, a matrix V cross V, a matrix T having a size V cross V, where T ij equals to 1 if there exists a path from vertex I to vertex j, from a path from vertex I to a vertex j. So, we represent this position as 1 in the case of adjacency matrix representation. And the second one is adjacency list representation. We can augment each vertex list with all reachable vertices. In sequential representation, an adjacency matrix is used to store the graph, where the linked list representation, there is a use of an adjacency list to store the graph. So, first we will cover adjacency matrix representation. So, a matrix V by V, V size matrix T, where T I j equals to 1 if there exists a path from vertex V I to vertex j. Suppose we have a undirected graph and we want to represent this graph in a form of adjacency matrix. So, we can create a matrix of size V cross V. V is a set of vertices 1, 2, 3, 4, 5. We have 5 vertices. So, we have 5 by 5. So, size of this matrix is 5 cross 5. It is a matrix of cross size 5 cross 5, or we can say V cross V. And now we have to fill the values in the positions of matrix. So, from A to A, there is no path or no connection between A to A, so a 0. A to B, we have a connection, so 1. A to C, we don't have any connection, direct connection, so we put 0, or we cannot put 1. So, there is only two chances, either we have to put 0 or we have to put 1. So, A to C, there is no direct connection, we have to place 0. From A to D, there is a direct connection, so we have to place 1. From A to E, there is no direct connection, so we have to place 0, or we can't place 1. Now, the same, now we have to explore B. So, from B, we have to search all other nodes that are directly connected with B. So, B to A, we have a direct connection, so we have to place 1. From B to B, there is no direct connection. B to C, 1, B to D, 1, and B to E, 0. So, by this way, we can fill all the values in this V cross V matrix tree. So, this is the case. Yeah, or suppose if we have a weighted directed graph, so how to represent adjacency matrix for this? So, if we have like this weighted directed graph, before this we just cover this directed. If we have a directed graph, so in the same condition, the directions are assigned for the edges. So, if we say from A to A 0, A to B a direct is 1, A to C no direct connection 0, A to D. So, there is no path from A to D or directed path from A to D. So, we have to assign 0 here. But in the same case, in the case of undirected graph, we are placed 1 here. But in the case of a directed graph, we have to place or put 0 in the position of AD, and from A to E no direct connection. As same, we have to follow for B. So, there is no connection from B to A, there is a direct edge from A to B. So, A to B 1, B to A we have to place 0, B to A 0 is this position. Same in the previous one we have placed 1, but not in this case because there is no direct connection between B to A. There is no direction of A's from B to A. So, like this, B to C 1, B to D a directed A's, so we have to place 1, B to E there is no directed A's 0. In the same case from the C, there is no connection from C to B, C to A no direct connection 0, C to B no direct connection or no directed A's from C to B 0, C to D no directed connection 0, C to E a directed edge, so we have to place 1. So, these two matrices are for the same number of vertices and for the same connection but a directed connection, and the positions are filled differently in between these two matrices. Now comes to this third case, a weighted directed graph where there is a weight associated with a edge. So, in the same case we assign a weights, this and this. These graphs are similar directions, but the directions or the edges contains weight here. So, we do not put 1, we have to put the weight of that particular edge. So, likewise we can say A to B we have a directed edge but with a weight of 4. So, we have to place 4 here. From A to C no directed edge, A to D no directed edge, A to E no connection, all entries are 0 except A to B with a weight 4. Next example or next case we have to cover B. So, from B to A there is no directed edge, from B to C are directed edge with a weight 2. So, we have to place 2 here, sorry. Now, from B to D we have to place a value 1, this, and B to E there is no directed edge, so we have to place 0 here. And likewise we have to fill all the values like C to E we have a directed edge and placed 8. All these values are 0 because there is no directed edge from C to any other vertex except E. From D we have to place the values, but there is only a single directed edge from D to A with a weight of 5. So this value D to A is 5. Now we have to cover E. So there is no directed A's from E to any other node except D. So we have to put the value of 10 from E to D. So likewise we have to fill the values in a matrix, or we can say we can represent this graph with the help of adjacency matrix representation. A way how to store values in a system or a computer memory. So first case. Second case is linked list representation, or we can say adjacency list representation. Adjacency list is used in the linked list representation to store the graph in the computer's memory. It is efficient in terms of storage, as we only have to store the values for ages. Let's represent, or let's see this adjacency list representation of a undirected graph. In this undirected graph, we can see that there is a vertex, or there is a linked list or adjacency list for every node of the graph. From vertex A, there are path to vertex B and D, a path from A to B and A to D. These nodes are linked to node A in the given adjacency list. A to B, A to B, and this is cross for the representation that this is the ending of this list. So adjacency list is maintained for each node presented in the graph. For A, adjacency list. For B, we have to represent a separate adjacency list. So for B, there is a node A and D and C. So from B, we can say there are 3 nodes directly connected. So we can represent adjacency list with respect to B, A, D and C, and end of the sign, end of the list, adjacency list. So an adjacency list maintained for each node in the graph, which stores the node value and a pointer to the next adjacent node to the respective node. And if all the adjacency nodes are traversed, then store the null pointer, or null in the pointer field of the last node of the list. So we have to assign null in the last node, and the sum of the length of adjacency list is equal to twice the number of edges present in an undirected graph. So this is a simple representation of a linked list representation, or we can say adjacency list representation of a graph. So we have covered A, B, C, D and E. Likewise, a directed graph and a very directed graph. So for all these two, in previous case, we have covered a undirected graph adjacency list. Now we have to cover adjacency list for a directed graph and adjacency list for a weighted directed graph. So for a directed graph, this is a adjacency list from A to B, a directed node. So there is no direction from A to D. So there is no uh, connection of node D, as well likewise from B there is a connection of C and a connection of D. So we have to link these two nodes C and D. Likewise from C a direct connection of E. Likewise from D a direct edge from A, and likewise from E we have a directed A's to D. So this is a adjacency list for a directed graph, and the sum of lengths of adjacency list is equal to the number of edges present in the graph. Likewise for the weighted directed graph, so we assign another field like the weight for the particular node. So for A to B we have a weight 5, same. So we assign 5 after B, position of the weight, same adjacency list with assigned edges weight here. So these are the weights assigned to particular edge in a weighted directed graph. So these two adjacency lists are same. This list is for our directed graph, or we can say a non-weighted directed graph, and this is the adjacency list for a weighted directed graph. Next, what is a spanning tree? A connected subgraph of S of a graph ZV, a graph connection of V, is said to be a spanning if S should contain all vertices of G. So S contains all vertices of G, and S should contain V minus 1 edges. It's called a spanning tree. A minimum spanning tree contains these two properties. S should contain all the vertices of G, and S should contain V minus 1 edges. So applications of these are to find out the shortest path from or the find out the minimum cost spanning tree in the graph.